Kaboom! This is Chemical Thermodynamics, Part 1, and you need to just kind of read this chapter with a little grain of salt. I'm Miss Bedrosian, and I'm going to try and decode the chapter for you and just go straight to the important parts. Spontaneous processes, also known as thermodynamically favored processes, can be fast or slow. Fast like a bunny, slow like a turtle. It's based only on the properties of reactants and products, unlike rate. Rate depends on other things, such as activation energy, temperature, concentration, etc. So we are looking at whether things are thermodynamically favored. Here's a little cartoon, some polar bears. And the reason why this is on here is that most people think most processes are exothermic, and many of them are. But some thermodynamically favored processes are endothermic, such as ice melting is one of them. So, all thermodynamically favored processes increase in entropy in the universe. And what's entropy? Entropy is a measure of disorder or chaos. This is also known as the second law in physics. Here's a cartoon of entropy getting more entropy. Now, don't panic. I know that the chapter has a lot of things in it about microstates and things like that, but in reality, you don't need to know those. S is a measure of disorder, or chaos, in other words. How messy is your room? How messy do things get after time? So S is a measure of disorder, and we have a nice little equation. Delta S of the surroundings is equal to negative delta H over T in Kelvin. If delta S is positive, meaning the surroundings is positive, then heat is flowing into the surroundings. The magnitude of this depends on temperature, obviously. So delta S is a measure of disorder. Now the following are at 25 degrees Celsius and 1 atm. And I'm going to give you two equations. Here's the first one. And I'm also going to give you delta H. Delta H is equal to negative 125 kilojoules. The second equation is as follows. And delta H for this one is a positive 778 kilojoules. Taking a look at this, you need to find delta S and determine if it's exothermic or endothermic. So do that math, please, and here comes the answers. For A, delta S would be negative 125 kilojoules divided by 298 K, and that's a 0.419 kilojoules per K. And what is it? This is exothermic because it's positive. You can do B. Here it comes. I'm going to show it to you. And this comes out to negative 2.61 kilojoules per K. And this one, because it's negative, must be endothermic. So I just want you to focus on S is disorder. The entropy of atom combination is the change in entropy when a mole of a substance is produced from its atoms in the gas phase at standard 1 atm and 25 degrees Celsius. Just a little bit to know about S is that the standard molar entropy, which is at 1 atm and 298 K, is written as S prime, it's called. This is called S prime. S prime increases if it is a gas, if it has high molar masses, and higher atomic numbers, which seems to go together. And most important of all, it is not easy to figure out S. It just ain't easy. There's no easy method. So using an equation that you've seen somewhat before, delta S prime is equal to the sum of NS prime products minus the sum of MS prime reactants. N and M are the coefficients from the balanced equations that we have done before. See how chemistry, what goes around comes around. We've seen this type of equation before. So here's the example. You need to calculate the standard entropy change, which is delta S prime. Here is the equation, taking a look at it. And if you looked in the back of the book and you looked up their enthalpies, you should be able to figure it out. Here it is all plugged in. And we've done this before. And the final answer for this is 180.39 joules per mole Kelvin, or joules Kelvin, because S prime is for a mole. So here's the truth about this chapter. The only thing you really need to know, besides being able to do this simple equation right now, is this table. Memorize the table on page 828, 19.4. That's what you need to know. That's it. Don't forget it. Memorize it now. Part 1 is done. Kaboom!